So in this video we will learn about some application of arbitrary uh, based on some augmentation of the arbitrary. So arbitrary is a data structure based on the binary search trees. So for different type of application we have to augment this data structure. Augmentation means we need to change the structure of a node, or we need to increase the size of a node in order to apply some efficient operation for the particular applications. Now we have to study dynamic order statistics and interval tree, which is based on the arbitrary, or we can say that which is that these type of problems can be efficiently solved by choosing the arbitrary as a data structure, because arbitrary is efficient data structure in the class of BSTs. So let's first discuss about the dynamic order statistics. So the dynamic order statistics says that for any given dynamic set is the set which the number of elements is maybe increase or decrease while the operation is applied on the set. Okay, so for a dynamic set, if we want to find out the kth smallest or largest element, so for find out the kth smallest or largest element on some dynamic set, uh, it requires or these types of problem can be known as dynamic order statistics. So for the searching of such elements we require a procedure known as OS select order statistics select procedure on some node I, which will return the ith smallest. So if I consider the smallest element, so it will return the ith smallest item in the dynamic set. Okay, so to solve this problem, suppose I just consider only one problem. We need to find out or the ith smallest element in the dynamic set. So the idea is we need to keep the size of the subtree in the node of the red black tree. So first is we choose arbitrary because it is a search query. So for the search query, for the efficient search query, the BST will be proven as best data structure, but the BST is skewed if the given sequence is sorted or in ascending or descending order. That's why we can use AVL tree also, but because it is a dynamic set, it may possible that number of insertion and deletions are maximum, so the AVL is not efficient. So the efficient BST would be arbitrary. So we choose arbitrary data structure in order to solve this problem of ith smallest, to find out the ith smallest item in the dynamic set. Okay, so the idea is we need to keep the size of the subtree size of the subtree in the node of the arbitrary. Okay, so for example, let me draw arbitrary for the same. Let me choose another color here. So suppose arbitrary with black. So this is the arbitrary node structure with the key value. I just store the size of a subtree, so I fill this one later. Let the left part contain the information C with some size, then A with some size, then at the right hand side of this one may contain some information F with some size, and on that left part there is information D with some size, and on the right part some information H with some size. Similarly here, suppose it is a P with some size, and Q, and here it is N. Okay, so this is the arbitrary. So for example, let me color this arbitrary because the all nodes are black. So because it is arbitrary, suppose for any configuration this node is black, this node is red, this is black, again it is red, and here it is black, and it is also black. Similarly these two are red and this is black, and all leaf nodes are sentinel nodes, so sentinel nodes are attached. Okay, so we need to, as we the idea is clear, we need to maintain the size of the subtree at each node. It means size of the subtree means the size of the left and right subtrees. So for the nil node the size of the subtree is 0, that is the base case. So the size of the subtree for node D is 0. So the size of this subtree can be filled as size of the left subtree plus size of the right subtree plus 1. Okay, so I can fill 1 here, left plus right plus 1, and I can also fill 1 here. Then for F it is 1 plus 1 plus 1, it means it is 3. Similarly for this one it is 1, for C it is 5, for this one it is 1 1, and I can fill here 3, and I can fill here 9. 5 plus 3 plus 1. So how I measure the size of any node X? So size of any node X would be the size of left of X plus the size of right of X plus 1. So this is the size which is maintained by each of the node. So the trick here is we use the size of sentinel node as a nil. So size of a sentinel node is equal to nil or 0. So size of a nil node is equal to 0. So I can also write here size of nil of T is always 0. Okay, so this is the idea. Now we use this augmented data structure of arbitrary in order to find out the solution of my problem, which is we have to find out the ith smallest item in the dynamic set. So let me write the procedure for the same. So I write the procedure here. We need to find out. So OS select I, it means this is the procedure which return the ith smallest element. So for this one, let me have a k variable which is which is having the value of size of left of X plus 1. Then if this value k is equal to I, then we return the node X, which is the ith smallest element. So return the node X. So here it is X, return the node X. So let me make it clear. I just delete it and make it clear. Okay, so yeah, so return the node X. If it is not equal, and if I is less than k, then if it is less than k, then we have to recursively call the same procedure os select on the left portion of the x. So left of x with the information I. If it is greater than the k, then it will return the os select on the right of x with the value I minus k. Okay, so this is the os select procedure. So now let's scan this procedure according to some given example. So if some dynamic set is given, then how we can find out the ith smallest element or ith largest element in the tree. Okay, so let me take an example. So suppose I take the previous example as I just redraw that example. So I just change the color. So suppose the information in the previous example is given as here it is m, then on the right side it is c, then at the right side it is a. So and at the sorry, it is at the left side. On the right side it is f and d and h are there, and on the right of m we have p, on the left of it we have n, on the right of it we have q. Suppose this is the example. So I make this m as a black. Okay, c is red, I leave it. A is also black, f is also black, and n is black, q is black. Okay, now I mark the red nodes. So the red nodes are the remaining nodes are the red nodes. So c is a red node, p is also a red node, d is a red node, and h is a red node. Okay, these nodes are given. Now let's write the size of each node. So here the size is 1, this node size is also 1, the size of f is 3, the size of a is 1, the size of c is 5, the size of p is 3, size of n 1, size of q is also 1, and the size of m is 9. Okay, so let's now link each of the node. So m is linked with c and p, and on the right hand part of c is f, f right is h, h right left is this one, and p or q is connected with this arrow. Okay, now some sentinel nodes are also there. So each last internal node have some sentinel nodes with the color black. So this is the given tree. In this tree, if I need to find out the fifth smallest element in this tree, so I just call the os select function on, suppose, on the root. So I just call the os select procedure, which is written earlier, on the root node with 5 information. 5 means I need to find out the fifth smallest element. So this os select will be called, which will find out the fifth smallest element in this tree. So this algorithm says that In order to find out the OS select this, I need to initialize the value of k, which is nothing but size of left of x. So x is root here. Initially x is root, so here x is root. So size of left of x plus 1 is k. So k would be 6 size of left of x, and if we check whether this is I is k, we check that whether I is equal to k. No. Then we check whether I is less than k. So I is less than k, yes. It means again the same procedure OS select will be called on what node? Left of x comma I. So now left of x comma I means this node C. So we will call OS select on the C with I value 5. Now at this node the value of k would be the left of x plus 1. So k is 2 and the value of I is 5. So we see that 2 is less than 5. 2 is less than 5. Yes, 2 is less than 5. So I need to check I is less than k. So whether 5 is less than 2. No, condition false. So condition false means it will go to the right part. So OS select will go to the right part. So I just use the short form OSS for the OS select, and the right of the C is F, and the right part for the right part the value of I which is passed here is 5 minus 2 means that is 3. So on the right part the value 3 will be passed. Similarly for this recursive call the value of k would be 2 and the value of I is 3. So 3 is less than 2. I check whether 3 is less than 2. It will say no, 3 is not less than 2. So go to the right part. OSS will be called on h comma 3 minus 2 means 1. Okay. Now again check for the k. K is equal to nil plus 1. It means k 1 हो गया, and the value of I is also 1. So I is equal to k. So for this case I is equal to k, it means this is a base case. It will return the x, and now x is value h. X is pointing to h. So now this node is returned. It means the fifth smallest element for this tree is h. So let's verify this procedure. So if I write the in-order traversal of this algorithm, so the in-order traversal of this BST is A, then C, then D. So I just go from left, parent, right, and right. In the right we go to the left, then parent, then right, then parent, then right, then parent, then right. Okay, so this is the in-order traversal of the tree, and in this in-order traversal we can see that 1 2 3 4 5th. At fifth position we find the h value. So h is the fifth smallest element in the tree. Okay, so this is how we can augment the arbitrary data structure in order to find out the fifth smallest element for a given tree. So let's do the some analysis of this algorithm. So for the analysis we can see that we need to run the OS select at most the height of the tree. So means OS select can be run at most log n time, so order of log n time. So the time complexity for the OS select procedure would be order of log n. It is nothing but order of log n. So this is about the analysis of search procedure on the augmentation. Now if we apply some queries for some sorry for instead of queries, if I apply some type of update operation or modifying operation on the same tree, then the modifying operations includes, so if I apply some modifying operations on the set data structure, modifying operations, so modifying operations include two operations, one is insert and delete. So these are the two modifying operations on any data structure. Modifying operations means these operations will change the orientation of the data structure. Okay, so let's take an example. What is happen when we insert any element into the arbitrary which is provided. Okay, so for example, if you want to insert a value k, insert a value k, because it is a BST insertion, the value of the k is inserted based on the comparison of the root nodes. Okay, so but here there is one more point which is need to be take care of. We need to update the size of each subtree. Okay, so we need to update the subtree sizes while we insert any new node into the augmented arbitrary data structure. Okay, for example, suppose the tree which is given as m with size 9, c with size 5, a with size 1, then here f with size 3 and d with size 1, here it is h with size 1, and in the right side of it we have p with size 3 and it is q with size 1, and on the left part we have n with size 1. Okay, so this is the tree. Let me color it because it is arbitrary. So some nodes are black and some nodes are red. So these two nodes are black nodes. The root is always black. Here this node f is black and this node a is black. Now I mark the red nodes also. So the red nodes are, the rest of nodes are red nodes. So these four nodes are red nodes. Okay, so this is my arbitrary. Now to insert any node into this arbitrary, I just see the root, whether the root information at the root is greater than or equal or less than the given key. So k is less than m, so it will go to the left part of it and the degree of this is incremented. Now we check with c, k is greater than c, it will go to the right part and it is increment the degree. So then check with the f, so k is greater than f, it will go to the right part, increment the degree. Then compare with h, k is greater than h, increment the degree, go to the right part, and here the k is inserted. Because this is a arbitrary, so it will follow the properties of an arbitrary, and the newly inserted node is always red. So I make this color of this node is red. Now instead of because this node will violate the property number 3 of the arbitrary, no two consecutive red nodes can be possible in arbitrary. So what we do, we just recolor or rotate the given tree. So based on the cases which is studied in the arbitrary insertion and deletion. Okay, so while we do the rotation, we need to take care about the size of the tree. So I will give you one example of the rotation. So suppose for a moment of time, a subtree with key information, sorry, I just deleted. So for example, a tree is given with size 16. The information is not provided yet. At the left of it, another node is given with size 11, and in the left of it we have different sizes of subtree. Okay, so if you want to rotate it from left to right, then this node this this node will become the parent, and this node will become the child of it. Okay, so let me change the color. So okay, now this node goes up and this node goes down. Okay, so here at the right of part it is 5, it will go to the right part of the previous node, and on left part of it we have 7. Let me delete this line. So at the left part of it we have node 7, and the 3 will be placed here. Okay, now we need to update the size of these two nodes. So 5 plus 3 means 8, so the size is here 9, and here 9 plus 7 means 16, so the size of this node would be 17. Okay, so here also it is 17 because 11 7 3 10 11 plus 5 16 plus 1, it is 17. Okay, so the root or the size of the root never be changed whether the rotation is performed. The size of the internal nodes is always changed while do the rotation. Okay, so the insertion will and deletion is also take order of log n time, because the height of the trees is still maintained in the log n way. Okay, so the rotation will take so insertion the rotation of this algorithm will take order of 1 time, because of the we just only shift the pointers. There is no modification in the height of the tree, we just shift the pointers in the tree. Okay, so the cost the worst case analysis of the insertion and deletion operation is order of log n. Okay, now next part is, if I can say that the augmentation step of any data structure need these following steps. So I just enlist the, if you want to augment any data structure, it means you need to take care about these steps. So I just write down here, for augmentation of any data structure, the points which is important are: first, choose the data structure, choose the appropriate data structure according to the application or the data structure which you want to augment. Okay, so choose the appropriate data structure. So in the previous application we choose arbitrary as the appropriate data structure. Second, determine the additional information. So we need to determine the additional information, some additional information about the data structure, like we use the subtree size in the previous example. subtree size. So this additional information is used. The third point is we have to verify that information. So verify that information can be maintained for modifying operation on the data structure, can be maintained. The information which is determined above can be maintained for modifying operations like insert and delete. So modifying operations, for example insert and delete, we need to maintain the information for these modifying operations. Okay, now then last point is we need to develop new operations on this augmented data structure. We need to develop new operations. So for example, if I augment the data structure with the size, the new operation is os select, that we have studied, os select on some node I. So this os select operation will find out the ith smallest element in the dynamic set. Okay, so this is all about the augmenting a data structure. Thank you very much for listening.